So, welcome back everyone. I hope everyone had an incredibly fulfilling lunch experience. And now it is my great pleasure to introduce our first speaker of the afternoon, Professor Doug Finkbeiner. Doug is faculty in the Department of Astronomy and Physics here at Harvard University and spent a lot of time looking at some incredibly interesting big data sets taken from the sky, including the Sloan Digital Sky Survey, WMAP, Fermi, and I'm sure other ones that I did not mention just now. So without further ado, here is Professor Finkbeiner.
All right, thank you. All right, good, that seems to work. So I will leave it up to you to decide whether what I'm talking about is big data or not. I think of big data not as a number of terabytes or something, but rather as a way of looking at problems. What you see behind the title screen here is a representation of the distribution of interstellar dust in our galaxy within a few thousand light years of us. And this is just the parallax shift you would see if you're going around the sun about 10 million times further than we normally orbit around the sun. So it's slightly exaggerated. And we'll get to how we make such maps. So first of all, why do we care about this kind of thing? Well, this is basic human exploration, right? We want to know how our galaxy is put together, where things are. This is part of a long-term project to map a lot of things in 3 dimensions. The density of interstellar dust, the gas density, both hydrogen and molecules like CO, which is the most important molecule for astronomers. That's easy to measure, I mean. We want to look at the density of stars and their dynamics, and that's really going to be a big growing industry in the next few years with the Gaia satellite releasing its data in coming months. That's making precise measurements of the positions and motions of 1 billion stars. And we'd really like to know about the radiation field of the galaxy in 6 dimensions. How much radiation is there in every direction, in every energy, in every volume element. So, but this stuff also gives me an excuse to talk about probabilistic catalogs, which we sometimes call PCATs, and transdimensional inference. So we'll talk about that. First of all, though, I just want to set this up so there's a little bit of scientific motivation for this. I want to tell you about interstellar dust, because that's what I've spent a lot of my career working on. So this is the stuff out there that's between the stars. It's not just empty space. It's not just a little bit of hydrogen and helium. There's actual material. It can be things like silicates, like beach sand, or carbonaceous grains. On the big end, we call those graphite, just a slangy kind of way. On the small end, we call them PAHs, polycyclic aromatic hydrocarbons, and those are a lot like car exhaust. Dust can look dark. Here's a famous dark cloud, Bernard 68. And you see, you really can't see through it, at least in visible light. You can in infrared. So sometimes dust looks dark if it's blocking the light, but it could also be scattering light if there's a bright star nearby. This is an example of the Witch Head Nebula scattering light from the star Rigel. In general, it's complicated. You have dust absorbing and scattering light. You'd like to take an image like this from a telescope. You'd like to learn about the brightnesses of the stars in here and the properties of the dust that are absorbing and scattering the light. So the general case here is very difficult, too difficult to talk about, too difficult to solve, but certainly too difficult to talk about today because this radiative transfer problem is a mess. But where we're going with this is different kinds of astronomers want different kinds of dust maps. People who study cosmology and want to look at the universe on the largest scales want to look outside of our galaxy. We live in this disk galaxy, right? If we look up and down away from the disk, we can see through the dust pretty well. The dust is optically thin. It's only scattering or blocking a few percent or 10% of the light. It's not as big a deal. If we look in the plane of the galaxy, then the optical depth can be 20 or 40 or something. And e to the minus 40 is a small number. So what do these things actually look like in practice? This is dust that we've actually gathered from our local interplanetary dust cloud in the solar system. And you see these Dust grains look like they're just a bunch of things that have been stuck together. I mean, if you took a bunch of sand and put it in a blast furnace for a while and partially melted it together, you might get something that looks like that. Or like that. This looks almost more like a chip of quartz that broke off of something. Actual interstellar dust is smaller dust grains than these, but we have a hard time gathering those. So the composition of this stuff is quite uncertain. We know there are some silicates and some carbonaceous grains because we see those features. There's probably silicon carbide and various ices and iron and so on. And so, you know, there are a million different things dust can be, and so you might think that modeling all of this is just completely hopeless and we can go home. But nature is often more kind to us than it needs to be. Ignore the crab. I'm pointing out the dust here, which is really cool. This is just beach sand. But you go to any beach in the world, and there's kind of a linear combination of some white grains and some clear grains and some brown and some black and whatever. And you know, with 4 or 5 numbers, you could probably do a pretty good job of describing the beach sand anywhere in the world. And so it's like that with the interstellar medium. It's sort of infinitely complex in detail, but we can actually get away with a simple approximation here. And so a couple of guys at Princeton in the 80s provided these efficiencies for absorption and scattering of different kinds of dust at different sizes. And we can actually just, you know, model an ensemble of dielectric spheres with some size distribution and the optical properties that these guys came up with. And it actually recovers almost everything we empirically know about dust. So it's in reality a very complicated problem, but we can do something simple. So we're gonna stay simple for the rest of the talk here. And we just boil the question down to how much dust is there along each line of sight and how far away is it along each line of sight. So to do that, we're going to use the wonderful feature of dust that it actually absorbs and scatters blue light more than red. This is related to the reason that sunsets are red and the sky is blue. All right, nothing profound here. So this is just optical depth over some measure of cross-section, doesn't matter, arbitrary units, as a function of the wavelength of light that's getting absorbed or scattered. So kind of infrared to ultraviolet here, and this is the visible spectrum we're mostly concerned with, but you know, astronomers observe across about 18 orders of magnitude in wavelength, so we're interested in everything. And so the fact that we lose more blue light than red light means that by the change in color of a star, we can say something about the dust. We don't need to care how far away the star is, at least at first. And star colors are near some locus in color space. So if we plot what astronomers call G minus R minus I, we get a stellar locus like this. So I should just be clear here. So astronomers are insane. They like to measure logs of everything. That itself isn't insane, but you could use natural log or something, but no, it has to be minus 2.5 times log base 10, which turns out to be close to minus natural log. So if you want to, just think of this as natural log. I think they chose this because back in the day when people were doing the math in their heads and they didn't have computers and they wanted something that was kind of close to a natural log, but also kind of, you know, easy. If this ratio is 100, you know, this is 5, right? It's easy to think about. So these color differences, because these are logs of the flux in green light and in red light, for example, this is actually logs of flux ratios. Okay, so you plot your stars, and they look like this. And these are just the stellar types that some other insane astronomer assigned things a long time ago. So if you watch Star Trek, and they say, oh, the sun is a G star, they mean it's about here on the color plot. Fortunately then, at least for the purposes of this talk, we'll pretend all dust is the same. It's really not, and we can map the differences, and they're really cool. But let's just pretend that all dust is the same, and it pushes you along this direction in this color space. And imagine, if you will, a much higher dimension color space, but I only have a 2D projector here. So we're going to slide along this direction if there's more dust. So let's take a close look at how this works. So here's the colors of a bunch of stars without dust and with some dust. See, it's very easy how that works. Okay, so that's literally what happens. The whole stellar locus just slides over. If you put the dust in front of all the stars. Of course, if the dust is only in front of some of the stars, some slide and some don't. We also know how bright the stars are overall, which was not represented in that plot. So you might think we can actually work something out here. The problem is, if you just take one star, you don't know where that star started on here. In particular, if it's kind of near this because of the direction of the reddening vector, there's a near degeneracy here, and because of noise, you can be confused. There's also the fact that if there's a star here, is that its color, or is it from over here, and the whole locus got shifted? So there are different kinds of degeneracies and ambiguities here. So one star does not teach you very much, but if you have 1,000 stars, all in a very narrow cone on the sky, so they're experiencing kind of the same dust along the line of sight, you can learn a lot. So the data we use for this comes from a project called 2MASS. It's a relatively small telescope on Haleakala in Hawaii, 1.8 meter aperture, but it has a big camera. This is the focal plane of the camera, and as you can see in John Tonry's arms here, he's a normal-sized person, and so the focal plane's like this big, paved with silicon. So 1.4 billion pixels. So it's, it's an interesting trade study. Is it worth making the telescope bigger and the camera smaller, or the camera bigger and the telescope smaller, or how do you spend your money? And this turns out to be fairly optimum to use a small telescope and a gigantic camera. That's me actually looking in the primary mirror taking my pictures. So you see the whole thing isn't really very big. So we measure the sky in 5 colors of light, known as green, red, infrared, even more infrared, and really, really even more infrared. And from these we can make images. This is about the size of the focal plane of the telescope. So one shot in 3 different colors of light could be used to make this image. And I'm going to zoom on this little area over here called the Trifid Nebula, just to see there's a fair amount of angular resolution. And you might think you can learn something about dust by looking at this image. Of course, I'm not actually going to use the dark dust lanes here amid the bright nebulosity to learn about the dust. I'm only going to use colors of stars, because these kinds of situations where you get good information about the dust this way are few and far between. I'm mostly showing this because it's a pretty picture. But we want to do this over the full sky. All right, so we're going to use the colors of the stars. So we've got about 800 million well-measured stars. And from these, we want to learn all these things. These are the former students and postdocs of mine who did all the work. Can't do it without them, of course. Greg just graduated and went off to Stanford just weeks ago. So we've got all these stars. Okay, 500 million, 800 million, whatever. We ended up using about 800 million. We can group them into fairly small pixels, calculate, that's astronomer jargon for distance, distance and amount of dust in front of each star, get a posterior on that, then combine those and ask what the amount of dust as a function of distance is along each line of sight. So in a little more detail, for each of these stars in our library, we're going to calculate this joint posterior on distance. This is really log distance in crazy astronomer units, and amount of dust, given the vector of magnitudes of the star we observed in the different colors. Okay, so there are things about where the dust is, where the star is, and then these are the observations. And a posterior for a good star, this is when things go really well. Your star looks like this, pretty tightly constrained in distance and amount of dust. So that model for the magnitudes, what should that be a function of? So to keep things simple, we'll just say we've got an absolute magnitude for the star. That's related to how big it is, how hot it is. It's just something fundamental about the star. And this ratio of iron to hydrogen, that's related to just how, the metallic content of the star, which will shift the spectrum around, shift the colors. And so we have models for these things. I won't go into detail about the models, but the models are based on, studies of millions of stars and are pretty reasonably good. So then what we've got, I won't have too many more equations like this, but our vector of magnitudes is there's some intrinsic magnitudes to the star as a function of the stellar type and metallicity. Then we get to add another vector here, which is how those magnitudes, those log fluxes, get shifted as a function of the amount of dust. So that's related to that reddening vector in color space I showed you earlier. And then this is just the log distance that gets added in because it affects all the colors of light the same way. So that's really all the model is. And then we have some likelihood of observations here that's just got Gaussian errors, a ball of Gaussian errors about that model. And so we use MCMC. We like the Goodman and Weir affine sampler, but you could use whatever you like. And we do this for many stars, like order 1 billion stars. We get a posterior for each one. Then we combine them in groups of 100 or 1,000 to define pixels on the sky. So these pixels have nothing to do with the pixels in the camera. They're pixels we're defining for regions of sky that we're interested in. And we do this for millions of pixels. So this was our first try. This is the amount of dust closer than 1 kiloparsec. A parsec's about 3 light years. So think 3,000 light years and 10,000 light years and 30,000 light years. Okay, and it does what you expect. The kind of higher galactic latitude stuff above and below the galactic plane are filled in first, and then the rest of the galactic plane fills in as you go out. We did this very early on in the project. You see the survey wasn't done yet, a bunch of missing data. This hole in the south is because if your telescope is in Hawaii, you can't see through the Earth. So there's some areas of the southern sky you can never see. This, I was attempting to play the movie. Okay. This is the same thing, just zooming in on a little patch of that sky. And as we go out in distance, it's the cumulative amount of dust. So we wrote some papers, and then we waited for the survey to actually be completed and ran things again, did a little better on the second try. So I'll just do grayscale now instead of the obnoxious rainbows. So this is 3/4 of the sky, now missing very little. Again, this is all entirely derived from the colors of stars. I'm going to zoom in on this region and then zoom in on this region just to show there's quite a bit of angular resolution there. And remember, this is a 3D map. That's just showing you 2D. But another way to look at it is take a patch of sky, show the cumulative dust as we go out in distance. And same thing as before. Same thing as before, the high latitude stuff fills in first, and then you'll see the galactic plane. Because it's further away, it's just a matter of perspective. Further out you go, the more of this fills in at b equals 0, which is the galactic plane. You may notice the pixels are flickering. I actually like this way of representing uncertainty, right? All of this information came out of a Markov chain. And I was at the Max Planck Institute in Heidelberg talking to David Hogg one day, and I said, I don't know whether to plot the mean, the median, the mode. What should I plot? And he said, just plot the samples. Why are you choosing? And that's right. Just make every frame of the movie a different sampling from the chain. And then it's actually doing exactly the right thing. When it flickers, that means the answer is uncertain. When the answer looks solid, it's solid. It's actually flickering the whole time. You just can't see the flickers because the variance is so small. So anyway, that's just something to think about in general. In images, we could represent our uncertainty by making movies. And then this is what I started with. This is just a very different way of looking at the three-dimensional nature of the dust by moving our perspective, moving our camera around and looking at the emission from the dust. Apologies, sometimes astronomers make dust black and sometimes they make it white. I think it has to do with whether you're thinking about the absorption of light by dust or the infrared emission from dust. A lot of people work on that, and so to them dust is bright. I guarantee you, when you write a paper that shows dust as black, the referee says you should have made it white, and then in your next paper you make it white and the referee says it should have been black. And this is an unsolved problem in astrophysics. Okay, so in one way this is a big data problem. There's about 1,500 terabytes of imaging boiled down to about 10 terabytes of catalogs, and we're inferring 80 million parameters for the 80 million volume elements of this map. And it takes about 2 million core hours to run. But is it really a big data problem? It's really the same little problem just done billions of times. It's straightforward and it's embarrassingly parallel. That doesn't mean it didn't take us years to do it, but it's, in the grand scheme of things, this is a very straightforward problem. So now let's push our luck a little bit here, because this is a big data conference and I want you to get your money's worth. So let's talk about photometry of faint stars in crowded fields. Like this. Well, actually not like this. This is simulated data. This is the trivial case. Reality looks more like this. This is a Hubble Space Telescope image of M68. And you see the point spread function of the telescope has wings. So you get these kind of big hazy regions around every star. There are diffraction spikes. So you see these crosses. They're most noticeable on the bright stars, but they are there for every star. It's just easy to see on the bright ones. So there are all those kinds of things that we can deal with. Astronomers have dealt with halos and diffraction spikes for decades. But just the sheer number of stars, it's easy to pick out a spot on here and ask, are there 5 stars in that glob, or 6 or 7? I can't tell, this is crazy. And this is with a telescope that has 20 times the angular resolution of the one we're using. Okay, so blur this by a factor of 20, and now tell me what the colors of all the stars are. So this brings up a good point then. There's a paper that's fairly well known among astronomers anyway, a few years ago, by David Hogg and Dustin Lang, and the title is Telescopes Don't Make Catalogs. It's really kind of true. Telescopes make images. They tell you about the distribution of light in a focal plane. They do not make catalogs. Astronomers make catalogs. And the catalog is seldom the interesting endpoint. It's seldom the goal of the study. The goal is to get some summary statistic. Maybe we want to know the luminosity function of stars. We want to know the 2-point correlation function of galaxies. We want kind of some, summary statistic that describes an ensemble of objects. We don't actually care about the catalog of objects. It's just a step along the way. And that's kind of a profound insight, because I think most astronomers out there would never think about skipping over the catalog step. Okay, but there may be reasons to. So when stars overlap, obviously things are more difficult. One thing is the positions and fluxes of neighbors are coupled, right? So there's this covariance between the flux and x and y of star 1 and the position and flux of its neighbor. And normal catalogs, you have, here's my object and its position and the uncertainties and the flux and the uncertainties, nothing about the neighbors. So how do you express these covariances that, may depend on the 10 nearest neighbors? There's not a good way, a good compact way to do that, the way astronomers conventionally do things. And then never mind the propagation of these uncertainties and marginalization over nuisance parameters. Every time you go and do photometry on an image, right, there's some point spread function here, right, the response of the optical system to a point source. These stars are point sources. I mean, their physical size is a billionth the size of what they appear on here, right? So they're all point sources. So you have all these nuisance parameters that describe the point spread function, the diffraction spikes, maybe there's some constant background offset in the image, who knows what. So you'd like to marginalize over those nuisance parameters, and the way astronomers traditionally do things, that's totally impossible. And sometimes, in some patch of sky, you can't even decide how many parameters there are. So we get into this problem of inference when the number of parameters to infer is something we need to infer. So transdimensional search. I know some of you in the room are quite familiar with this, but because some of you may not be, let's consider a toy problem here. So suppose we have a set of samples of some process, x of y and y of I. We want to fit a piecewise linear function. We're going to do this with the usual Markov chain procedure. We'll start with some parameters, propose new parameters, evaluate some new test statistic like delta log likelihood. So forget about the priors for now, and accept the proposal if it's better, and accept it with some probability if it's worse. So here's my piecewise linear fit to some points, and I'm gonna vary the parameters around, and then maybe I'll change the number of parameters, maybe I'll change it back. Okay, so the jumps that change the number of parameters are transdimensional jumps, right? You're changing the dimension of your parameter space. We don't know how many parameters are required when we start. We don't even know how many required are required when we're finished, right? It's a distribution. But we want the fit to tell us. Now, if I go back 20 years to some simpler problems we were doing in grad school, what one would do is add degrees of freedom until chi-squared per degree of freedom stops getting better, and then quit. That's not a good procedure in general, but there's some intuition about that that's actually not crazy. You want some penalty for adding new parameters, and you have to make sure you do that right. So how do we generalize this? So being good Bayesians, we have to include this equation, where we have the posterior is the likelihood times the prior over the evidence. And the evidence, of course, is just the integral of this thing over all parameters. So that normalizes this and makes this integrate to unity, which is a good thing in a probability. The problem is if you change the parameter space, you change this integral. So normally we just ignore this and we put a twiddle here and we say everything's fine because this doesn't change as we change the parameters theta. But if we change the model space, it does change. So we should actually write something more like this. There's nothing new here. This was new to me in recent years, but of course people have been writing things like this down for 20 or 30 years. I just didn't know about it. So we've got the probability of having some model and the parameters given that model, given the data. So that's what we're interested in. The likelihood is the probability of the data given the model and its parameters. We have a prior that we have that model at all, and then given that we have that model, the prior on the parameters that go with that model, right? And then that's all normalized by the evidence, which now depends on the model. So that evidence now is this integral here that normalizes that. But did I think I left prior on model. Oh, but this is given the model. I think I left a term out. Anyway, the point is this integral changes as we change the model. So we have to be careful here as we jump from one model space to another. If we have nested models, this is actually pretty easy. But in general, it may be more complicated. And we may actually want some kind of Occam prior on the number of parameters. And that's something I want to come back to at the end. There's a lot of confusion about that. Well, maybe not in the field, but at least in my head. But I think maybe in the field also. But let's just try this. So this is actually part of a much, much bigger image. I'm just zooming in on a little spot here. I had my students, Stefan Portillo and Ben Lee, run something that Brendan Brewer worked out called the diffusive nested sampler. It's a nice sampler to use in these kinds of problems on this sort of probabilistic catalog model. And so they're inferring the positions and fluxes of hundreds of stars in this image. And they sent me some results. And I said, oh, guys, you screwed up. Here's this place where there's obviously only 2 stars. And you found they're finding the red X's. So you find 5 stars that are always there and 6 or 7 in general, and there's only 2. So go find out why you're oversplitting and get back to me. But we had chosen this field because it has Hubble Space Telescope data. This has been done with data from the Sloan Digital Sky Survey, which is a ground-based telescope with, again, a points red function about 20 times blurrier than Hubble. So that means we have truth, right? We know the truth from Hubble. We're just trying to derive things from this horrible blurry image and see what we can get. So they went and looked at Hubble. So I should explain, first of all. So the red crosses are from our procedure. Blue is someone taking the Sloan Digital Sky Survey data and doing the best they can with the best high-powered astronomy tools. Actually, the standard Sloan pipeline that was run on the whole sky completely fails in this field and gives no answer at all, so I had to use something else. So the blue crosses are kind of the best that conventional astronomers can do. We got the red. That seemed crazy, but then we went and looked at Hubble, and that has the green crosses. The size of these crosses is related to the flux, maybe the log flux of the objects. So that was amazing to me. I don't know which of these to pick. Actually, I can zoom in the next frame. If we just stack our posterior for a bunch of samples from the catalog, you see, not very well, sorry about the projector, you see some green crosses here, and our clouds of red crosses are just our posterior stacked. That star we missed entirely, but it's very faint. It's so faint, we really shouldn't have gotten it. So the point is, every place we have a bunch of red crosses, there is actually a star there, observed by Hubble. So we actually got the right answer for some variety of right. Sometimes our answer is kind of bimodal, which is interesting. I don't know, what if there are actually two stars there? That would be amusing if Hubble couldn't tell. But I was amazed by this. You know, maybe once a year or less, your student sends you a plot and you go, oh, that's the plot of the year. Okay, this is the plot of my year. It is unbelievable that you can take an image that looks like the grayscale behind this and say, oh yes, of course, there are 7 stars there, with the right fluxes even. Okay, so this stuff actually works, even though we don't fully understand what we're doing. It seems to actually work. So let's talk about this prior on P of n a little more. I have to stop soon. So we may literally have a physical prior on P of n because we know something about the universe. So n here is just the number of stars in the image, let's say. So we may have a prior on that, but let's just keep that separate. I'm talking about a separate factor that we have to multiply in. So detailed balance of these transdimensional jumps means when we're jumping between models with different numbers of stars, the relative evidence we get in each of those subsections of the model is actually automatically normalized correctly, right? So we can kind of ignore that evidence ratio in the equations I was showing you earlier. But can we, right? As you add new parameters to a model, obviously you get a better fit. It's hard to get a worse fit. I mean, I guess if there are certain constraints on your parameters, but in general, you always get a better fit when you add new parameters. And so, so you want some way that the fit is penalized and doesn't use too many. You want the fit to be parsimonious. And so this idea of natural parsimony, of the fact that if you introduce new parameters and their prior doesn't fit them all that well, you know, if the prior is not that great, the fit will be discouraged from using those new parameters. This is an argument made in the Sambridge et al. Paper where he stole a figure from McKay, just showing that, so here we have a tight prior as opposed to a broad, less informative prior, and you know, the less informative your prior is, the worse your evidence will be, and that's supposed to be doing something to guide the model in the right direction, not use too many parameters, especially if they have lousy priors. But even if they have good priors, right, even if your prior on your new parameters is exactly right, you still want some penalty. So, and I just started jokingly calling this an Occam's prior, and then I noticed that papers for at least a decade have called it an Occam's prior. So what kind of Occam's prior is justified here? So if you go look up AIC, it advocates maximizing this. So in my simple Gaussian toy problem I was talking about, the likelihood is just a Gaussian, it's e to the, you know, it's just a chi-squared problem. It's e to the minus chi-squared over 2. So I could take the log of that, that's chi-squared over 2, multiply by 2, so I have minus chi-squared, and I'm maximizing instead of minimizing, so that all makes sense. The only difference is I have 2 times the number of new parameters penalty each time I add a parameter. That's actually a little different than my naive expectation. I mean, I can read Wikipedia, I know how to derive this formula, but my naive expectation was if you add a new parameter, the chi-squared on average gets better by 1. And so I would have expected 1k, not 2k. So then the question is, whatever choice we're going to make here, whether it's 1k or 2k, should we put this in by hand in our prior on the number of parameters? Just bake it in to our problem? Or is that somehow coming out by the natural parsimony of the evidence, effectively penalizing new parameters? So I have to admit, I am confused about this, and I'll bet someone in the room knows a lot more about it than I do, so feel free to send me an email. But I will just wrap up my talk now by saying that I think for astronomers, and probably in a lot of other contexts, there's a huge advantage to thinking of a catalog not as a list of objects and their uncertainties, but as an ensemble of catalogs, each of which doesn't have uncertainties, because the uncertainties are just in the ensemble itself. And this is exactly analogous to 20 years ago, people were telling us, oh, you won't just compute a mean and a variance anymore. You'll keep the whole distribution. You'll keep samples from the whole distribution. Well, that sounded insane. That's going to take up way too much disk space and everything. So this sounds insane to people now. I say I don't want a catalog, I want 1,000 catalogs. And they're all realizations of, they're samples from the space of all possible catalogs that are consistent with the data. It's a fair draw. And then I know how to, I can be very explicit about my priors and hyperpriors. I can keep track of all the covariances. I can marginalize over all the nuisance parameters. I can do everything exactly right. It's all beautiful. It's a lot of computational time and storage. And if you actually do want the catalog for its own right, its own sake, this makes your life more difficult. And sometimes you do, right? We do photometric surveys to pick interesting objects to go take spectra of. That usually involves drilling a hole in a sheet of aluminum. And I can't drill 0.7 of a hole. I have to decide yes or no, I want that object or not. So we can't completely get away from deciding on a specific list of sources. But I think it's true for most problems in astronomy. We're not interested in the catalog. We're interested in things derived from the catalog. And keeping this intermediate catalog step as a statistical ensemble really makes a lot of sense. So I'm betting this is how we do a lot of things in 10 years in my field. So I'll stop there. Thanks. Yes, sir.
Just in response to your last question, we do have a couple papers on these predictive error measures, and the short answer is that they can be things like AIC, which need to be generalized to work in Bayesian models, can be thought of as approximations to the point-out cross-validation, and from there, there you can get some insight as to where that factor of 2 comes from, and also work out some of these other things.
Okay, good. Yeah, I'd love to talk to you more about that. These are not the kinds of things that astronomers usually wade into, right? So I have no formal training in statistics, but we're trying to take what look like powerful ideas and bring them into the field of astronomy so people can use them. But astronomers, I'm afraid, are generally 20 years behind. Any other questions or comments? You survived a talk on interstellar dust, though.
Thank you.
Oh, thank you.